The physical properties of metals include two of the most important physical properties: good conductors of electricity and good conductors of heat. All right. Now, good conductors of electricity and good conductors of heat, these are properties for all metals. Let me please take this down. All metals have these properties: good conductors of electricity and good conductors of heat. So there are no exceptions to these rules. Okay, all pure metals will be good conductors of electricity and heat. Now, besides that, besides the conduction of electricity and heat, metals in general should have high melting points and high boiling points as well. However, for this, there is an exception. Okay, so group 1 metals do not have a high melting point. So group 1 metals like sodium, potassium, they do not have a high melting point. All right. Similarly, high density does not apply to group 1. Okay, so you can see a group 1 is a bit of an exception to some of these properties here. So you do need to know which properties applies to all metals, which properties does not apply to all metals. Okay, and finally, we come to the last physical property, which is malleable and ductile. So we have gone through in class. This word malleable comes from the word molded. All right, molded. So malleable means it can be molded into different shapes without breaking. So for metals, they can be molded into shapes like rods, bars, sheets, foil, without breaking. Now, the word ductile comes from the word drawn. It can be drawn or pulled into wires without breaking. Okay, so these are the typical physical properties of metals. Now, some of these physical properties that you can see here are very, very much applicable to what their metals are used for. So for instance, good conductor of electricity, that's why metals are used in your electrical wiring, electrical circuits, right? Things like malleable. Okay, malleable means can be molded into different shapes. That's why metals can be used as, let's say, aluminum foil. You can mold aluminum into a sheet called a foil, right? So this tells you that aluminum is malleable. All right. Now, but metals beyond these properties, you realize that metals which are pure tend to be rather soft and rather weak in terms of strength. Okay, so that is not always good. It's not always good that metals are soft and metals are weak. So we need to find a way to make metals stronger and harder. And the way to do that is to make an alloy. So an alloy is a mixture of a metal with other elements. Okay, so we need to know this concept of an alloy. So an alloy is a mixture of a metal with other elements. What that means is you need one metal and some other elements to mix with it. So at least must have one metal inside the mixture. So you need to know some common examples of alloys. The first common example is steel. Steel is made up of iron and carbon. So you can clearly see that the metal here is iron, but it's mixed with carbon, which is a non-metal. So iron and carbon are mixed together to form steel. Next, brass. Brass contains copper and zinc. And finally, bronze is made up of copper mixed with tin. Okay, so these are the three common alloys for which you have to know the elements present inside them. So steel is iron and carbon, brass is copper and zinc, finally bronze is copper and tin. Okay, now besides knowing the elements present in alloys, you need to be able to draw alloys as well. So over here, I've drawn a diagram of the particles present in an alloy. You can take a closer look at it, but immediately you spot that there are different atoms present. right? Now, this makes sense because alloys are mixtures of a metal with other elements. That's why you will have different atoms mixed together in an alloy. So you need to recognize that this is a diagram of the particles in an alloy. But besides that, you also need to be able to explain why alloys are stronger and harder. Okay? So to explain why alloys are stronger and harder, we use the 3Ds. Namely, they have different size atoms in the alloy. Some atoms are bigger, some atoms are smaller. Next, because you have different size atoms, it disrupts the orderly layered arrangement of atoms. Okay, it's a bit like the concept of the atoms getting stuck. Because you have different sized atoms, basically there's some blockage, there's some stuck. Okay, they can't easily form layers. It disrupts the orderly layer arrangement. And finally, the last D, because there's no orderly layer arrangement, it's difficult for the layers of atoms to slide over one another easily when a force is applied. All right. So this is the explanation why alloys are stronger and harder. The 3Ds, okay, so different size atoms in the alloy. It disrupts the orderly layer arrangement, and therefore it's difficult for the layers of atoms to slide over one another when a force is applied. Okay, so this concludes the very first part, which is about physical properties of metals and also mixture of a metal with other elements called alloys. Okay, so you need to be familiar with both of the physical properties as well as the alloys, and also with how to draw an alloy and how do you use this drawing to explain that alloys are stronger and harder than the pure metal. So now from the physical properties, we shall move on to the chemical reactions of metals. Now, there are 3 different chemical reactions, but before we get to the reactions, let's go through the reactivity series of metals. Now, this chapter is called Reactivity Series of Metals because we recognize that metals have different reactivities. Some are extremely reactive. They are very, very violent when they react. They may explode. Some other metals are very unreactive. They do not react with water. They do not react with acids. So there are different reactivities. Hence, we can actually order the metals into a series called the reactivity series. And shown here is the reactivity series. Now, for those on the Zoom meeting right now, I would advise you to copy out the reactivity series. Try to use landscape mode when copying so that you have more space on the right-hand side to copy down the reactions. We will summarize the 3 reactions of metals onto the same reactivity series. So place the reactivity series on the most left-hand side of your paper so that you have space on the right-hand side to copy down the reactions. So this is the reactivity series. I'm sure you recognize this. It starts with potassium right on top. Okay, so at the topmost position, you have potassium metal. This tells you that potassium metal is the most reactive. If it's on top, above, that means it's more reactive. So potassium is the most reactive amongst these metals here. On the other hand, right at the bottom of the reactivity series, you have gold. Gold is the least reactive metal in this series. Okay, so please spend some time to take down the reactivity series first, including the 2 elements carbon and hydrogen. So when you memorize the reactivity series, you should memorize it along with carbon and hydrogen in the series because it will help you frame your understanding of various reactions. Okay, so the first reaction of metals is the reaction of metal with water. Now, the water we are referring to here is cold water, water that is not heated up. So metal plus water forms the metal hydroxide. So this is an important word, hydroxide. You get the hydroxide when it's water. So for instance, if I were to react sodium with water, it produces sodium hydroxide, which is NaOH. All right, so sodium plus water forms sodium hydroxide. So if I have used potassium and water instead, that will form potassium hydroxide. If I had used calcium, then it's calcium hydroxide. Okay, so the idea is if it's water, we form the hydroxide. Now the hydroxide has important properties because we know sodium hydroxide is an alkali. If it's an alkali, the pH value is more than 7. In the case of sodium hydroxide, the pH value is actually quite high. It is around 12 to 14. It's very, very alkaline. What this means is that if I were to put universal indicator into the solution at the end, the universal indicator should turn violet or purple. Okay, so it should be purple or violet with universal indicator if the universal indicator is added. Okay, next, you realize that it produces a gas as well. So this reaction produces hydrogen gas. So what is the test for hydrogen gas? The test for hydrogen gas is to insert a lighted splint, and the lighted splint extinguishes with a pop sound. So these gas tests are also covered under the chapter on acids and bases, which you can go back and revise the revision video for chapter 8. Okay, so all in all, metal plus water forms the hydroxide and hydrogen gas. Okay, the hydroxide is an alkaline solution. Now, which metals can react with water? The metals that can react with water are the first 4. That means from potassium, sodium, calcium, and lastly, magnesium. So magnesium is the last metal that will react with water. Okay, now we will move on to steam. Metals can also react with steam. Steam basically is H2O gas. All right, so steam is H2O in the gaseous state. So it is important to take note of the state symbol of steam. So if you were asked to write the equation for steam and with state symbols, you need to know that steam is actually gaseous H2O. Now, when it's reacting with steam, the metals now form the oxide. So they do not form the hydroxide, they form the oxide. So for instance, let's say magnesium. If it was magnesium reacting with steam, Mg solid plus H2O gas, because it's steam, it forms magnesium oxide, which is a solid plus hydrogen gas. Okay, so the product form is now the oxide, magnesium oxide in this case, because you use magnesium metal. Okay, so which metals can react with steam? The ones that can react with steam are from potassium all the way to iron. So the metals from potassium all the way down to iron are able to react with steam. This means that magnesium can react with steam, zinc can react with steam as well. Okay, so magnesium reacts with steam to form magnesium oxide and hydrogen. Zinc reacts with steam to form zinc oxide and hydrogen. Okay, now potassium also reacts with steam. Of course, potassium is the most reactive in the reactivity series here. However, we usually do not do the reaction of potassium with steam. The reason is because potassium reacting with steam is explosive. If the reaction is explosive, it is not safe to carry out, and therefore we do not do it. Okay, so we need to know the metals from potassium all the way to iron are able to react with steam to form the metal oxide and hydrogen gas. Okay, so we have just covered the reactions of metals with water. and metal with steam. So 2 reactions already. The third reaction is the reaction of metal with acid. Now, as we learned in the previous chapter on acids and bases, metal plus acid forms the salt and hydrogen gas. Okay, so for instance, if I were to use magnesium again, magnesium plus, let's say, hydrochloric acid, that forms magnesium chloride aqueous plus hydrogen gas. Okay, so this is a typical reaction that you have done before in the lab. Put magnesium into hydrochloric acid, there is effervescence of hydrogen gas, and you form magnesium chloride. So last lesson, we did the revision for acids and bases. We also wrote this equation out. But the idea is, do all metals react with acids? Of course, the answer is no. By looking at the reactivity series, we can work it out. Some metals do not react with acid. The metals that do not react with acids are copper, silver, gold. So copper, silver, and gold, they are unreactive with acid. Okay, they do not produce any hydrogen gas. There is no effervescence or bubbles produced when you put copper into the acid. Now, how is this related to their position in the reactivity series? So you can see copper, silver, gold, their position in the reactivity series is actually below hydrogen. So we can conclude metals that are positioned below hydrogen do not react with acid. So if they are below hydrogen, they do not react with acids. And that's the reason why we include hydrogen in the reactivity series. Because hydrogen tells us which metals can react, which metals cannot react with acids. So if it's above hydrogen, like zinc, iron, they can react with acid. If it's below hydrogen, below like copper, silver, gold, they cannot react with acid. They do not produce any effervescence when you put them into the acids. Okay, so this is how we relate the acid reaction with the position of the metal in the reactivity series. Okay, so far we have looked at 3 reactions of metals with water, with steam, and with acid. So the very last reaction that we will look through is displacement reactions. So this is a type of reaction that we did in class. We have said that a more reactive metal can displace a less reactive metal from its compound. So for instance, magnesium. We know that magnesium metal is more reactive. On the other hand, copper is less reactive than magnesium, right? So what will happen in such a reaction? At first, the less reactive copper is bonded to sulfate. At first, copper and sulfate are together. Then we put in the more reactive magnesium. The more reactive magnesium, what it will do is it will grab the sulfate. So magnesium grabs hold of sulfate. And the effect of that is to displace, is to kick copper out. So the less reactive metal is displaced by the more reactive metal. So we can say that magnesium, being more reactive, displaces copper from copper to sulfate. Okay, so this is how we phrase the sentence. Magnesium, being more reactive, displaces copper from copper to sulfate. So this reaction will work only if the more reactive metal is added in as a metal. So if I were to reverse the order, will this reaction take place? Can copper kick magnesium out from the compound? The answer is no, this will not work because copper is less reactive than magnesium. So if copper is less reactive than magnesium, it cannot displace magnesium from magnesium sulfate. So it is important to recognize what have you added in. Is it able to actually kick out the other metal which is inside a compound like magnesium sulfate? Okay, so in this case, if I put copper metal in, the copper metal is less reactive than magnesium. It cannot kick out, it cannot displace the magnesium inside the magnesium sulfate. Okay, this also tells you a more reactive metal really wants to form a compound. Magnesium really wants to grab sulfate. It will hold on to sulfate more readily than copper will. Okay, so magnesium and sulfate really want to stay together. Copper cannot displace magnesium out from this very stable compound. Okay. Now let's move on to the next section on extraction of metals. Now metals are usually found on Earth as ores. Ores are rocks containing metals, but a metal is rarely found on its own. The metal would have reacted with oxygen in the air to form oxides, for example. So most of the time, the metals are present as compounds, not as elements on their own. Okay. In fact, of this entire series of metals, only the last one, gold, is uncombined, meaning it's found on its own as an element. So only for gold can you find gold metal on its own. The rest of the metals which are more reactive than gold, like silver, copper, and so on, they would be found as a compound. So for instance, copper is found as an oxide, copper oxide. Okay, so how then can you extract the metal, take the metal out from the compound? Because we need the metal, right? We want good conductors of electricity. So you will want to extract the metal out from the compound. And the way to do that is, of course, reduction with carbon. That's one good way to do that. Basically, you use carbon, you heat up the metal ore with carbon. So we say it's extracted by reduction of the metal oxide with carbon. What does this actually mean? Now, I will just demonstrate. For instance, let's use zinc as an example, Zn. If I were to react zinc oxide with carbon, this will produce zinc metal plus carbon dioxide gas. Of course, this equation is not balanced. To balance this equation, I will need to add a 2 in front of the zinc. So 2ZnO plus carbon forms 2Zn plus CO2. Okay, so what has happened here, if you look closely, is that carbon has taken the oxygen away from zinc, right? So carbon snatched over the oxygen. Now, this looks a little bit similar to the concept of displacement that you saw just now. Basically, carbon snatches the oxygen and leaves zinc all alone as the metal. So effectively, one way to see this is that carbon is able to reduce zinc oxide. Carbon is able to displace zinc from zinc oxide. Okay, so this method of using carbon to reduce the metal oxide works if the metal is located or positioned below carbon. If the metal is below carbon, it can be extracted by reducing the metal oxide with just carbon, because carbon can displace the metal from the metal oxide. Okay, so this method of extracting zinc using reduction with carbon is very common. So zinc oxide is commonly found in a rock. So all you need to do is just go to the rock, get the zinc oxide out, and then you heat up the zinc oxide with some carbon. Okay. Now you might ask, why carbon? Carbon is a readily available, very abundant substance. Okay, carbon can be found in your pencil lead. Carbon can also be found in charcoal that you use for barbecue. So all these are forms of carbon that's readily available to us. And as it turns out, carbon is a very useful chemical because it's able to extract metals which are below carbon in this way. Okay. So now we have settled gold right at the bottom of the reactivity series. It's uncombined. And we have settled the metals below carbon in the reactivity series. We just need to extract their metals from the metal oxide by heating or reduction with carbon. How about the metals which are above carbon? So for instance, we have potassium, sodium, calcium, magnesium, aluminium. If they are above carbon, what that means is that they are very, very reactive, right? So carbon will not be able to displace them. Carbon is not able to reduce the metal oxide. Carbon cannot reduce the metal oxide. Carbon cannot displace these metals from the metal oxide. Okay? And this is also because these metals, obviously, they are very reactive. Potassium is very reactive, sodium is very reactive. So they form very stable compounds. And because of that, in order to extract these metals from their compounds, we need to break down the compound. And the way we break down these compounds of sodium, potassium, is we need to use electrolysis, basically using electricity to break down the compound. So for these metals above carbon, we need to use electrolysis to extract them because they are very, very reactive. Okay? So this is the idea and the concept behind how extraction of metals is related to the position of the metal in the reactivity series. Specifically, we are looking at the position of the metal. Is it above carbon, very, very reactive? Below carbon, not so reactive, can be used carbon to reduce the metal oxide. Now, the very last part of this chapter on reactivity series of metals is the rusting process. Now, you might have heard of rusting in your daily lives already. Rusting is a process of corrosion. What does corrosion mean? Now, first things first, we need to know rusting applies to iron metal. So iron metal undergoes rusting. So what happens is iron reacts with water and oxygen to form rust. Rust basically is iron 3 oxide. Okay, now the color of rust, I'm sure you're familiar. You have seen rusty equipment, rusty tables and chairs before. Rust is reddish brown in color, right? It's reddish brown because it contains iron 3. Now, iron 3 means Fe3 plus. Oxide is O2 minus. So the formula is Fe2O3. That's iron 3 oxide. Okay, so Fe3 plus, O2 minus. Therefore, to balance out the positive and negative charges, we need 2 Fe3 plus, 3 O2 minus. That's why it's Fe2O3. Now, so for rusting to happen, clearly, you will need the iron to react with water and oxygen. The reaction of a metal with water and oxygen can be called corrosion. So this word corrosion just means that the metal reacted with water and oxygen. So with this, what are the conditions needed for rusting? The conditions needed, there are 2 of them. The first one is, of course, presence of water. If there is no water present, for instance, if I put the iron into dry air has no water, therefore the iron will not rust. Okay? Obviously, in Singapore, our air is not dry. Our air is very humid. There is water vapor in the air. And therefore, iron will rust even if it's placed in air in Singapore. The next condition for rusting is the presence of oxygen. Oxygen is found in air. All right. So you just need oxygen in the air as well as water vapor in the air for the iron to start rusting. Okay, so these are the two conditions needed for rusting to happen: presence of water and presence of oxygen. So now that we know this, how can you prevent rusting? So one good way would be to paint. If you paint the iron object, the paint basically forms a layer that prevents water and oxygen from coming into contact with iron. Instead of painting, you can also put a layer of oil or grease. So oiling or greasing is the same thing. You are putting a layer of oil onto the iron. It prevents the iron from coming into contact with water or oxygen. Another way to do this, we could use plastic covering. So instead of oil or paint, you put a layer of plastic. Finally, the next method which you need to know is this. Another very common way of preventing the rusting is to use the iron as stainless steel alloy. That means you mix the iron with some elements to form stainless steel. Stainless steel is resistant to rusting. That means it will not rust. That's why it's called stainless. Now, stainless steel is resistant to rusting because it contains iron mixed with chromium. Chromium is another metal in the periodic table. Now, what's interesting about chromium is that chromium reacts with oxygen to form chromium oxide. The chromium oxide forms a layer on the stainless steel to prevent the iron from rusting. Okay? Now, you don't have to know the exact mechanism of how the chromium oxide works, but it's important to recognize that stainless steel is an alloy that is resistant to rusting. Okay? So now, you must think through, okay, so if rusting needs water and oxygen, an iron object will rust if there's water and also if there's oxygen. Okay, so to prevent rusting, we just need to put a layer of paint, a layer of oil, a layer of plastic, or in the case of stainless steel, actually it's an alloy with chromium in it. And the chromium forms a layer of chromium oxide, which protects the iron from rusting. Okay, so this is the gist of what you need to know about rusting of iron. So remember, you need both water and oxygen to rust. If any one of these two conditions is missing, it will not rust. So if the iron object is painted, it won't rust. If you place the iron into boiled water has water, but there's no oxygen because the boiling process removes any dissolved oxygen. If you put the iron object in dry air has oxygen, but it doesn't have water because it's dry. So you just need to think through. If you need both water and oxygen, then it will rust. Okay? If you do not have either one of the two, it will not rust. Okay? And that is all you need to know about the rusting of iron. Right? And that really brings us to the end of the revision for the chapter on reactivity series of metals. So if you look back, there's just 4 sections. The first section is on physical properties of metals and alloys. The second section is on chemical reactions of metals. The third section is on extraction of metals. And finally, this is the last and final section on rusting of iron, which will require both water and oxygen. Okay, so that really concludes our revision for chapter 12, reactivity series of metals. Please rewatch this video so that you are better able to internalize all the concepts, which will be important for your assessments. Okay, thank you.